Good morning, all of you. My name is Ashutosh Rastogi. I'm a teacher by profession. My mission is to impart quality education to all. For that purpose, I'm creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos. Anyways, in our last lecture, we were discussing about stability theory. We have mentioned that we actually study stability in two parts. Number one is your absolute stability and another one is your relative stability. So we'll continue our discussion with absolute stability. So these are the outlines of today's lecture. We'll start up with the introduction, in which we'll try to sum up whatever we have learned in our earlier lectures, that how positions of poles actually affect the stability of any system. Then we will give the statement of Raud-Servets stability criteria. Then we'll try to find out the methods how you're going to generate basic Routh table. Then we will discuss few examples how we're going to create a Routh table. Then Routh array special cases. Then at last we'll discuss about application of Raud-Servets criteria. We basically split up this complete lecture into two parts. So about Routh array special cases and application of Raud-Servets criteria we'll probably discuss in our next lecture. So here is the introduction. Stability is the most important system specification. Obviously, if system is not stable, it will not going to produce the expected outcome. So if the system is unstable, its transient response and the steady state errors are insignificant points. An unstable system cannot be designed for a specific transient response or steady state error requirement. Therefore, stability is very important for any system to ensure that it can behave as it is designed. In other words, we can say that it should produce some desirable outcome. Obviously, if system is unstable, we cannot predict the system output. And if we cannot predict the system output, we do not have any idea how our system will going to behave. And if it is not producing some predictable output and it is producing some unwanted outcome, it is of no use. So we have discussed that the position of poles closed loop transfer functions gives the important information about the stability of the system. In earlier lecture, we have studied that if closed loop system poles lies on the left side of the S-plane, then our system will behave as a stable system. If it is on the right half of the S-plane, obviously poles, if the positions of poles lies on the right side of the S-plane, then system response will be unbounded and system behavior will be unstable one. And if the system poles lies on j omega axis, then system will be marginally stable. This is what we have studied in earlier lecture. So obviously, hence with proper information about the system poles and their positions, we can perform the stability analysis of any given system as we mentioned just now. If it is on the left half of the S-plane, system will be stable one. If system poles positions lies on the right side of the S-plane, system will be unstable one. And if it is on the j omega axis, then it will be your marginally stable system. So if we represent a closed loop transfer function as journal polynomial in S, then the coefficient polynomials can give the information about the positions of roots. This is your journal polynomial theory. We have already studied in our 11th, 12th standards some equations of parabola, that what are the roots of that parabolic equations, where they actually lie. So this is the basic idea behind the Routh criteria of system stability. So here we are with Raud-Servets stability criteria. So it is the method for determining the system stability. Obviously, we are discussing about the absolute stability of the system. So what was his statements? Raud-Servets criteria states that the number of roots of the characteristic equation with positive real parts is equal to the number of change in sign of the first column of the Routh array. So obviously we have to discuss how we're going to generate this Routh array, but its statement was the number of roots of the characteristics equation with positive real parts, which actually creating our system unstable, is equal to the number of sign changes in the first column of the route array. This method yields stability information without to need solve for the closed loop system poles. It means we are only concerned about the positioning of system poles. Where they actually lie, we do not need to solve out those equations appropriately. We are only concerned with the positions of poles, so that we are in a state to comment on the absolute stability of the system, whether the system behavior will be stable one or unstable one. So with the help of this method, we can tell how many closed loop system poles are on the left half of the S-plane, or in the right half on the S-plane, or on the j omega axis. Here one thing should be noted very clearly, that we are saying how many poles. We are not saying where they lie on the S-plane. Obviously, we do not need to solve the actual positioning of the poles. We are only concerned with on which part of the S-plane they actually lie. Whether they are lying on the left, they are lying on the right, or they are lying on the j omega axis. We are only concerned with that, so that we could comment that the system behavior or how system will behave, whether its response will be a stable one or unstable one. So the route method requires two steps. Number one is generate a data table that is called route table, and the second part is interpretation of that table to tell how many closed loop system poles are in the left half of the S-plane, in the right half of the S-plane, or on the j omega axis. So the complete procedure actually requires these two steps in order to find out the absolute stability of the system. So we'll progress with the first step, how we're going to generate basic route table. So first of all, write the denominator polynomial of the closed loop transfer function in the following form and equate to 0. Obviously, this particular form. This generalized characteristic equation is of the form just like a0 s to the power n plus a1 s to the power n minus 1 plus a2 s to the power n minus 2 up to an that is equal to 0. One thing should be noted properly, that a of n should not be equal to 0. That is, we have to remove any 0 root. So first label the rows with power of s from highest power of s down to the lowest power of s in the vertical column. Next, form the first row of the route table using the coefficients of denominator of the closed loop transfer function, which is your characteristics equation. I think it is become little bit complex, but we'll try up to explain it with some examples or some equations, so that we'll try to make it clear. So you start up with the coefficients of the higher power and skip every other powers of s. Now from the second row with the coefficients of the denominator skipped in the previous step. The table is continued horizontally and vertically until zeros are obtained. For convenience, any row can be multiplied or divided by a positive constant before the next row is computed without changing the values of the rows below and disturbing the properties of the route table. It means, just for simplicity, we can multiply or divide any complete row with a positive constant so that calculation may get easier. So obviously all those procedures are little bit quite cumbersome. So we'll try to simplify it. Let us understand what we have learned so far. So what we have said is, we are making a column s to the power n, s to the power n minus 1 up to s to the power 0. Then we'll write up the coefficients and skipping every other coefficient of s. It means s of n in correspondence to s of n, we'll write up a0, a2, a4 and s to the power n minus 1 corresponding to s to the power n minus 1, we'll write a1, a3, a5, a7 up to till end. So first two rows, it is quite easier. By simply checking the characteristic equation, we may write first two rows of the route table. Then the question is, how are we going to create or complete route table? So let us say s to the power n minus 2, the corresponding coefficient terms are b1, b2, b3, b4 up to end. Then s to the power n minus 3, these are c1, c2, c3, c4. These are the coefficients, and we need to find out these coefficients. What will the value of these coefficients? So again, e1, e2 corresponds to s of 2, s of 1 for f1, and s of 0, the coefficient is g1. Then what will be the value of b1? How are you going to find out the value of b1, b2, b3 or c1, c2, c3, c4, e1, e2? This is what we have to perform. So what will be the value of b1? b1 is equal to a1 times of a2 minus a0 times of a3 divided by a1. This is what will be the value of b1. And for calculating the value of b2, we have to multiply a1 into a4, then a0 into a5 divided by a1. And for again b3, we have to do a1 into a6, then a0 into a7 divided by a1. This is what we have mentioned till now. The value of b1 turns out to be a1 a2 minus a0 a3 divided by a1. Then b2 is a1 a4 minus a0 a5 upon a1. Then b3 is a1 a6 minus a0 a7 divided by a1. And this complete procedure will keep going on till we get the 0 rows. Similarly, for c1 turns out to be b1 into a3 minus a1 into b2 divided by b1. Then c2 is equal to b1 a5 minus a1 b3 by b1. So we have to keep doing this exercises on and on till the time we'll get the 0 at the lowest or at the bottom. So this process continues until the nth row is completed. So now second step is table interpretation. How are we going to interpret this formed table? How are we going to interpret that our system will be a stable one or unstable one? So the system is stable if there are no sign changes in the first column of the route table. Please keep in mind, while performing this complete route stability criteria, we are only concerned with the first column of the route table. We just only need to check out number of sign changes in the first column of the route table. We do not have any importance of the other rows of the route table. So the Routh-Hurwitz criteria declares that the number of roots of the polynomial that are lies in the right half of the S-plane is equal to the number of sign changes in the first column. It means as many number of sign changes we'll have in the first column of the route table, that number of roots lie on the right side of the S-plane. And we know it very well, if roots lies on the right side of the S-plane, then our system behavior will be unstable. So whether it is one pole lie on the right side of the S-plane, or 2 or 3 or 4 or n, then in that particular case our system behavior will be an unstable one. So the system is unstable if the poles lies on the right hand side of the S-plane. This is what we have already studied. So let us take a simple example. Suppose in this particular transfer function, which is represented by this ns upon a4 s4 plus a3 s3 plus a2 s square plus a1s plus a0, input is rs and the output is cs. We have to specify that whether the system represented by this transfer function will be a stable one or unstable one. Since we are interested in the system poles, we focus our attention on the denominator. We will not going to consider or focus over this numerator or zeros part of the transfer function. We'll only concerned about this lower portion of the transfer function. Only the first two rows of the array are obtained from the characteristics equations and remaining are calculated as follows. This is actually we had already discussed, but with the same examples we'll try to check it out, that how are you going to frame simple Routh table. So this will be the figure of complete Routh-Hurwitz table. S4, S3, S2, S1 and S0. This is what we have to write out. Then the coefficient of S4 is A4, then skipping every other coefficients A2, then skipping other coefficients A0, then A3, A1 and A0. With the help of simple characteristics equation, we can easily form first two rows. Then what will the value of B1? Simply A3 into A2 minus A1 into A4 divided by A3, that will the value of B1. And similarly, we can say that B2 is A3 into A0 minus 0 into A4 divided by A3, that will the value of B2. Then value of B3 will be 0. It should be B3. A4 into 0 minus A3 into 0 upon A3, that will be 0. And similarly for C1, C2 and C3, we can simply evaluate the values of Routh table. Then D1, and for the same manner D3, D2 and D3. So this is how we are going to generate the basic Routh table. So let us take a quick example how we are going to create Routh-Hurwitz table. Suppose the system transfer function is given to us is 1000 over s plus 2 into s plus 3 into s plus 5. ES obviously is the error signal, CS is the output and RS is the input. This is the unity feedback system, negative feedback system. So first of all, we need to find out the closed loop transfer function of the system. Obviously this is your GS and HS is equal to 1. Then we have to calculate the complete closed loop transfer function, which is equal to GS over 1 plus GS into HS, and we'll be having this complete closed loop transfer function whose input is RS and output is CS. So obviously we have to focus on this denominator polynomial S3 plus 10S plus 31 S plus 1030. So complete Routh table will be given by coefficient of S3 is 1, then skipping the next coefficient we'll be having 31, then 0, and for S square we'll be having 10, then 1030, 0. We had also mentioned that for simplicity we can easily divide or multiply our complete row by any positive quantity. Suppose that will be dividing by 10 this second row, then we'll be left with 1, 1030, 0. So then what will the value of next coefficient? Obviously 1 into 31 minus 1 into 103 divided by 1. This is, and we are left with minus 72. Then the next coefficient value is 1 into 0 minus 1 into 0. Again that will be 0. And the next coefficient is 1 into 0 minus 1 into 0 divided by 1. That will also equal to 0. So for the next coefficient, minus 72 into 103 minus 1 into 0 divided by minus 72, that is again turns out to be 103, and next two values are becoming 0 and 0. This is the complete Routh table. Let us quickly discuss through an example. We have to determine whether the following polynomial has a roots in the right half of the S-plane or not. The polynomial is S4 plus 2S cube plus 3S square plus 4S plus 5 is equal to 0. This we could also say that this is the characteristic equation of our system, and we have to evaluate whether any roots of this particular polynomial lies on the right side of the S-plane or not. So as we have discussed earlier, we have to create Routh table first. So we have to write down decreasing order power of s, obviously s to the power 4, s cube, s square, s1 and s0. First two columns we can easily write 1 s to the power 4. The coefficient of s to the power 4 is 1. Then skipping next coefficient will be having 3. Then skipping next coefficient will be having 5. Then the coefficient of s cube is 2. Then skipping next this 3 will be having 4, and then it is 0. So now next question is how we will going to evaluate the coefficient of s square, or the third row, the first column element. So which is found out to be 1 and 5. How will get that? So for evaluating this one, will be having 2 into 3 minus 1 into 4 divided by 2, which turns out to be 1. 2 3 is 6 minus 4, that is 2. 2 by 2 is equal to 1. Then how are you going to get this 5? Again 2 into 5, 10 minus 1 into 0 divided by 2 turns out to be 5. Okay. Then what will be the next row? This turns out to be minus 6. How are you going to get that? 1 into 4, 4 minus 5 into 2, 10 divided by 1, that turns out to be minus 6. Again next value will be 0. Then how are you going to evaluate the coefficient of s0? Minus 6 into 5 minus 1 into 0 divided by minus 6, that is turns out to be 5. So this is how we are going to create or develop complete Routh table. So since two sign changes are there, therefore two poles lies on the right side of the S plane. How we are saying that there are two sign changes? Plus to plus, then again plus, then plus to minus, that is your one sign change, and minus to plus, that is your another sign change. So there are two sign changes, plus to minus and minus to plus. That is why we are saying that there are two sign changes, and there are two poles that lie on the right hand side of the S plane. Hence the system will be your unstable system. So these are the references that we have discussed while preparing these materials. Thank you very much for your patience here.